In this lesson, we will discuss inclined tube manometers. If your device will experience small changes in pressure, you might not be able to measure that pressure change accurately with manometers that use vertical tubes. This is because the fluid level in the tube will change by only a small amount, and you will be limited by the accuracy of your ruler or whatever you use to measure the length. However, if we tilt the tube at an angle theta, the fluid level would rise vertically by the same amount, but would travel a longer distance along the tube. So if the fluid level were initially at the red dashed line and an increase in pressure moved the fluid level to the purple line, notice that the distance L is greater than the distance H. So inclined tube manometers can measure small changes in pressure more accurately than manometers that use vertical tubes. If the angle theta were very small, the fluid would travel a much longer distance along the tube. That is, L would be much greater than H, which allows you to more accurately measure small changes in pressure. The other end of an inclined manometer could be exposed to the ambient environment, or could be connected to another device. In this image, two sections of pipe are connected to each other with an inclined manometer that has a gauge fluid. The manometer is inclined at an angle theta. The specific weight of the fluid in the devices is gamma 1 and gamma 3, while the gauge fluid has a specific weight of gamma 2. Points A and B are at the center of the two sections of pipe. Point C is located at the same elevation as point B, and point D is at the interface between fluids 2 and 3. Point G is located at the same elevation as point A, and point F is at the interface between fluids 1 and 2. The vertical distance between point A and the interface of fluids 1 and 2 is the height h1. Point E is located at the same elevation as point F in the gauge fluid. The vertical distance between point B and the interface of fluids 2 and 3 is height h2. The distance along the tube between points E and D is length L. Now we will determine the pressure difference between points A and B using hydrostatic principles. We start at point B and will work our way around the manometer until we reach point A. The pressure at point B is PB, and the pressure is unchanged as we move horizontally to point C. Moving from point C to point D, the pressure increases by gamma 3 times the vertical distance h2. Notice that the distance between point C and D is longer than h2, but pressure only varies in the vertical direction. As we travel from point D to point E, the pressure increases by gamma 2 times the vertical component of L, which is L times sine theta. We jump across to point F without a change in pressure because points E and F are at the same elevation, then move to point G while the pressure decreases by gamma 1 h1. Finally, we move horizontally from point G to point A with no change in pressure. We have reached our destination and set the equation on the left equal to the pressure at point A. Rearranging the equation, we have an expression for the pressure difference between devices A and B.